You got any little ones?
Well, and I emailed that little.
Ones to see in person that
Yeah.
I'd love to see them up close. We have an artist in residence here who's already selling her work. You may want to go ahead and get her autograph because you never know on the road show. It might be worth a lot. I saw a little picture last night worth $80,000 that somebody said. My mom just had it hanging in her trailer, and I thought, man, she could have sold that picture and had it. The mom didn't know what it was. I thought she could have sold it and put that trailer at the beach. Mountains. Okay, welcome back everybody. We are now at Lecture 9 in Math 131, Lecture 9, and we're moving right along. One of the things we need for using derivatives for curve sketching is to recall how to solve some inequalities. So I just have one simple one for us to do where we use a sign chart to figure it out because we need it. We need to finish our drill that we didn't in Lecture 8, Chapter 2, Section 2 on page 159, so go ahead and have your books there, a couple problems from the exercises. And then I like to combine Chapter 2, Section 3 and 4 because it's all on using the derivatives for curve sketching, and it just works so well to sort of have a little cookbook and do it all at one time. Your book will do one little part of the curve and not the whole thing. And then the next section it'll do a little bit more. And so I like to just do it all at one time because you've learned the terminology. We already talked about what the derivative tells you, and we'll work from there. We got quite a few examples. So hopefully we're going to get through 2.3 and 2.4 today. And I'd like to begin section 2.5. These are your applications to the derivative. Applications to the derivative. And this is not on Vista, but I pulled it up. I don't even know if you can see it. Probably can't. Can I make it big? View. Well, I don't even know how to make it bigger here. But anyway, on Vista, there's a supplement for optimization problems. The thing on the bottom right. That would be down here?
No, leave the mouse on the words and then pop up.
Here?
Right there in the corner.
Right here?
Yeah.
You are good, good, good. Let's do that again. It's not going to let me, is
It'll
it?
just make it small.
Oh, okay. All right, so thank you very much. Math 130, get out of the way. Okay. All right, believe me, it says supplementary optimization problems. Going to have that on Vista to give you some extra drill. What I like about that is I have grouped them by types. They're a little bit interwoven in your exercises, and we're going to only focus on 4 types, and that way I have them organized. Geometric is problems 1 through 5. The next part is maximizing a yield or a revenue or something like that. That's problems 6 and 7. And then 8 and 9 are called inventory problems. And then the other has to do with cost, profit, revenue. And but anyway, once we start this, I'm going to label these are the 4 types. The supplement here has 3 of those 4 types. So because I always felt like if you drilled on this kind, then you started to feel good, and then drill on the next kind of group them together. So that supplement is on Vista. All right. Okay, so let's begin. We want to do just a quick warm-up with solving inequalities, which we will need. So we just want to do a little quick review. And we want to solve this inequality over the real numbers. Solve the inequality. And that inequality is 3x squared minus 6x greater than 0. Okay, so we're looking for all the values of x that make this a true statement. All right, how do you start out solving an inequality, everybody? Yeah, we want to factor. You start out trying to treat it like it's an equation because you got to get the boundaries of your inequality based on what makes it equal to 0. Because on each side of what makes it equal to 0, then it's going to be greater than or less than. So just like when you solve an equation, you would want to factor completely. So let's factors. We have 3x times x minus 2 greater than 0. Right? Okay, and we're going to use what's just called a little sign chart, number line with the sign chart to help us solve it. So first we look at what makes it equal 0. We're not going to have that as part of our solution, but we need it to be able to check around the intervals. So what makes it equal to 0 is when x equals 0 or what x equals 2. Okay, so we'll just come over here. Here's our little number line. X equals 0, x equal 2. We know that's not part of our solution because it doesn't say greater than or equal to. And just give you a heads up, remember when your derivative is greater than 0, if you have a function, it tells you it's going to be increasing, right? So we'll have greater than zeros, less than zeros, equal to zeros for possible extreme points when we do derivatives. All right, so what we're asking is if I pick a number bigger than 2, because bigger than 2, it will never equal 0 again, or we would have found it when we were solving this. So any number bigger than 2, the inequality has to always be positive or always be negative. So a number bigger than 2 might be 10. Just pick anything bigger than 2. You could put 2.1 in if you want to, but I just get way over here. So we're looking in the interval bigger than 2. If I pick a number bigger than 2, 3x is positive. 3 times 10 is positive. 10 minus 2 is positive. A positive times a positive is a positive. So I'll just put a big plus there. If I pick a number between 0 and 2, an easy number would be 1. So if I put a 1 into 3x, that's positive. 1 minus 2 is negative. So a positive, it's called sign, S-I-G-N, because it's either positive or negative. We're just looking at the negative or the positive signs. Okay, so if you put a 1 in, it's positive times negative. Positive times negative is negative. Okay, pick a number less than 0, such as negative 1,000. 3x times negative 1,000 is negative. Negative 1,000 minus 2 is negative. Negative times a negative is a positive. Okay? So the question is, where is it greater than 0? Where is it positive? Well, it's positive. You know, you can do interval notation, whatever you want to do. It's going to be positive coming from, how do you write it? Negative infinity up to 0, parenthesis. Suppose that had been or equal to 0. We would have used a square bracket. Okay. And then you use like a little union sign, or you could say or, it's here, or it's over here. And then we pick up at 2 and we go to positive infinity. Okay, remember inequalities? The big deal is getting a 0 on one side to solve an inequality, because you're still using the rule A times B equal to 0. Then A is 0 or B is 0. But if you have a number here, it doesn't work, because there's a zillion things you can multiply. Zillion's not a word. Many things you can multiply together to give you 0. I mean, give you another number. But for A times B 0, one of those has to be 0. Everybody got it? Okay, the other thing that I want to point out to you before we get into optimization, and I want to point it out early so you'll be working on it, is textbook chapter 0. Remember your review chapter 0? And the 6, section 6. You're going to need to spend a little time here. Take my words of wisdom. You need to spend some time here. This is the basics for the optimization problem. I'm in chapter 0, section 6, functions and graphs in applications. And we're going to be applying the derivative. So we got to be able to write the function that goes with the particular situation. And they actually have it set up here for geometric problems in the beginning. You need to write down the problems, try working them yourself, and they're worked out for you. Very, very important. Almost make you want to hold your hand up and promise to work these out, because they're going to show up in optimization, and so if you don't have the basis, it's going to be hard. Surface area, you'll remember that's how much material it takes to make a box area, the sides of your box or your can or whatever. Surface area, how much materials it takes. You've got your business problems, cost, profit, revenue, with some examples. Okay, let's see what else is in here that I want to really point out. I think page 51 is a good place to look. It has a type of applied problem, and then it gives you like a function that goes along with it, maybe the graph for interpreting. But see, we're going to use curve sketching to help us interpret functions. Okay, and another place to look for some more drill is in the exercises. You have a rectangular box with a square base. Can you find the volume of that? Can you find the surface area of that? You have what are called little right circular cylinders. Those are your soup cans. And these have bottoms and tops. And as we work a couple problems in class, for sure I'll mention those formulas to you again. But all this is here. You want to spend some time getting there. And it's got a lot of good problems here. You cannot spend too much time in this section because mastery of this is necessary for applying the derivative, because it's going to be these types of functions that we're going to maximize the volume of or minimize the surface area. Or we're going to have our little fences here, and we want to maximize the area with some fences, or etc. Okay? Everybody really understand? I think it's very important you spend some time in section 6. All right, I'll send around the red pen. Write it in your notes. Go to chapter 0, section 6. Okay? All right, so we are now going to finish cleaning up where we were yesterday. And let's just say where we were yesterday. We're in section 2.1 and 2.2. We were using words and symbols of derivatives to mean the same thing. When we had a function that increased, we know it just means basically somehow it's going up. Okay, it might go up, concave up. It might go up concave down, concave up, or straight, but it's increasing. So when we use derivatives for increasing functions, we know the slopes are positive, right, if they're increasing. So our symbol will be that the first derivative equals 0 for increasing functions. So for whatever values, greater than. For whatever values of x makes that derivative greater than 0, like this little sign chart we just did, we know our graph's going to be going up. We don't know the shape yet. Whenever it's decreasing, we know that it's going down. We know the derivative then, which is the slope of curves going down, is negative. Wherever we have a first derivative equals 0, somebody tell me the big important word with that. Yes, we have possible extreme point. If your curve goes from decreasing to increasing, then you're going to have a minimum, relative minimum. It might not be the absolute. If it goes from increasing to decreasing, you know you have a relative max. It might be an absolute max, but we know it's a relative max for sure. So that's called the first derivative test. You got to check on each side to determine if at 0 it is an extreme point. All right. So the first derivative really only tells you, does the curve go up or does the curve go down? All right, so first derivative is up or down, or straight, I guess, horizontal asymptote. All right, now we're going to put shape to the graph, the concavity. All right, so you have concave up. Concave up means that your slopes are increasing. Your slopes, which is a first derivative, increasing slopes. So increasing means, remember the derivative up here is greater than 0 for increasing. So now we have the slope by taking a derivative greater than 0 would mean increasing, slopes increasing. So that's how you get second derivative of x greater than 0. That tells you concave up. The little tangent lines are underneath. Concave down, the slopes are decreasing. Slopes decreasing, decreasing, slopes decreasing. That's a second derivative less than 0. So concave up holds water, tangent lines are underneath. Not really holds water, but some people like to look at it. Concave down, your little tangent lines are drawn on top. Concave down. So this is only going to tell you first find does it increase or decrease, and then go back over it and add shape to the graph. What's it called when you have a second derivative equal to 0? Possible inflection point. Possible inflection point. Inflection point is where the curve changes from concave up to concave down or down to up. Okay, so, but just because the first derivative equals 0 does not mean for sure it's an inflection point. You have to check. Where do people really mess up on tests? I'll give you a problem. I'll say find the inflection point if it exists. They go take a second derivative, set it equal to 0, and say that's it. What did they forget? To check it. Does it go from down to up or up to down? Just because the derivative equals 0, that's not a guaranteed inflection point. Sometimes I'll say find all extreme points. Students on tests will just go set a first derivative equal to 0 and come up with the points. And we go minus 8 out of 10 because you don't know if that's an extreme point or not. You haven't checked to see does it go from increasing, decreasing, or decreasing to increasing. Right? Everybody got it? Make yourself a note. Keep marking those red pens. All right, let's go to section 2.2 and finish those up, and then we're going to have fun putting it all together. 2.2. Okay, I believe that we want to start with problem number 14 on page 159. Please use your book. Please read the examples in the book. Write them down, cover up the work, practice, 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 then check your book. Wear that book out. You paid a lot of money for it. All right, exercise 14. We're going to use the information to make a good sketch of the function very near x equals 3. All right, we just want to know when we get to the point where x is 3, what does the graph look like very near 3 and through 3? Okay, make a good educated. All right, we'll do the first one together. When you see f of 3 equals negative 2, what are you given? Point. All right, so let's start making a little list. We have point 3, negative 2. When x is 3, y is negative 2. What does it mean when the derivative at 3 equals 0? Okay. This point is a possible extreme point. Okay, we're getting that from the derivative equals 0. We also know what kind of tangent line is there. Horizontal tangent line. Okay, I'm just making little notes as I read. So when you see these symbols, start putting them in words. All right, so we got the point. We know when the derivative is equal to 0, this point is going to be a possible extreme point. For sure, we got a horizontal tangent line there. Okay, now the next little part says the second derivative at 3 is a positive 1. Concave up. So we know there it is, concave up. This 1 is not a big to-do factor at the second. It just tells you how the slope is changing there. But the main thing is the second derivative at 3 is positive, so we have now a point. We have a possible extreme point there, and we know it's concave up. Can we draw the curve near the point? Yes. Okay. All right, so I'm just going to take all this information. Here is the point 3, negative 2. All right. So I got the point. I'm going to put a little horizontal tangent line there because for sure it's a horizontal tangent line, right? A little we have to stay near the point. Now we're not spreading this out all over all values of x. It just says give us a little sketch very near that point. So I'm just making a little horizontal tangent line. Okay, now from this point we also know it's going to be concave up. So how am I going to get a concave up here with a horizontal tangent line? What's it going to look like? Yeah, a little parabola coming through here like this. All right, that's all we need to know. Because if it's going to have a horizontal tangent line and it's got to be concave up there, that's the only thing I can possibly do. So actually that ends up being an extreme point, right? It's going to be a relative minimum since it's at the bottom of the little parabola. Okay?
I understood that wrong. I thought at 3 or 0, I thought 3, 0, that's where
Oh, okay. You said f prime of 3 equals 0. You thought that's a point. No, it's a derivative.
okay.
The derivative, I appreciate you saying that. Okay. This just says when x is 3, the slope of the curve there will be 0. So when x is 3, the slope of the curve there will be 0. Thank you, because somebody else probably thought the same thing too. Everybody good? Okay, now I want you to do number 16. Problem number 16. F of 3 equals 4. The derivative at 3 is negative 3 halves. The second derivative at 3 is negative 2. All right, I think it's very helpful if you use words and then do your sketching. And let's put somebody's paper up so we'll learn from each other. Who's got it? I definitely want to put yours up so that I get it. That is so good. Proud of you. Actually, I'm going to take hers because it's already done. Is that okay? I still might want to show yours though. Hey, you know what? I do want to show your red. Anyway. I just wanted to show this. Remember I passed around the red markers? The student wrote area max, know it or fail. Thank you very much. That should alert you to do that. To go back to section 06. Thank you. You guys are good, good, good. Okay. This particular person also wrote in red practice and wrote the page down sections. All right, but I wanted to get to this problem and look at the words. All right, so let's look at it together. First of all, f of 3 equals 4. Everybody knows that's a point, the point 3, 4. So 3, 4. I know we were quickly doing this, but you want to sort of label your axes. All right, because the derivative at 3 is negative, she knows the function is going to decrease in there. Now the only thing, do you care if I write on this? The only thing that she knows from that piece of information is that she just has a straight line going down. She doesn't know the shape yet. Okay, so you got a straight, if it's decreasing, just put a line going down through it. Now the second derivative will give you the shape. And because the second derivative is negative, we know it's concave down. So we just go over something that's decreasing and smooth it around to make it concave down. Perfect. How'd everybody do?
Just draw just a line. Didn't need to put like arrows at the end of the line or anything.
What, here?
Yeah.
No, actually, when you sketch a curve, you really don't have to. If you have a restricted domain, you put a big dot there to indicate it stopped. But without it, it just goes on forever, both directions. Okay, everybody good? Perfect. You guys are doing good. We pass that back down. I was going to send you to problem number 19, but we need to move on. Number 19 refers to figure 18. You've got the answers in the back of the book, but spend some time with that. Spend some time with it. All right, we are going to have fun now. We are going to Chapter 2, Section 3. We're going to put it all together. So what we had was 2.1, the words, increasing, decreasing, concavity, extreme points. 2.2, we had the symbols that gave us what that looks like in a visual. Now we're going to take the function and we're going to figure out everything ourselves and sketch the graph. All right? So we're going to start out with something we really already know the graph of. All right, so the instructions are use derivatives to sketch the graph of, and we're going to pick something easy that we already know answers to. What it looks like. F of x equals x squared minus x minus 6. And then we'll build on that from there. All right? All right, go ahead and tell me what this is going to be the graph of. Parabola opens up. Y-intercept is -6. All right. So I have sort of a little cookbook method I go through, and you're welcome to do that. The main thing is, can you answer all the questions that I give you, like what's the first derivative tell you and all this stuff. But here's my little cookbook, and it always seems to work well. I always start out with any restrictions on the domain, because if you have some vertical asymptotes, you need to know what they are right away. It's always easy to find the y-intercept. And you only do that if it's easy. Oh, that's easy. But the x-intercept is not always easy. So the x-intercept's if easy. But don't waste any time there, because a lot of times they're real numbers. You can't find them anyway, or you may not have any x-intercepts. Okay? So let's set up our coordinate system, and we're doing good curve sketching. So you spread out your units. This is not the place to be sloppy. Label your axes. You're going to have to make it very clear if you have a curved sketch on your test, because if I can't tell if it's concave up or concave down, I can't guess. 1, 2, 3, 4, 5, 6. Okay? Just set up a coordinate system. Spread out your units. Label your axes. All right. What is our domain for x squared minus x minus 6? Are you restricted? Is there any division by 0? No, yeah, so we know it's just going to be all real numbers, so we're okay. What's our y-intercept? Okay, y equals -6 is y-intercept. So as soon as you find something, my recommendation is to go plot it. Okay. All right. In this case, are the x-intercepts easy? Yes, because it factors. So in this case, it's easy. So we'll say x squared minus x minus 6 equal to 0. That's where y equals 0. Solve for x. So x minus 3, x plus 2. So the x-intercepts are at 3 and -2. Okay, so we'll plot x at 3, x at -2. And I know in pre-calculus you learned how to graph this without using derivatives, but we're just going to use them to so you see how they work. Okay? All right. Now, when you get ready to sketch, don't you need to know where it goes up and down and possible extreme points? So the second thing we need to do, oh, and I forgot to mention in here, are there any asymptotes? And we do very little in Math 131 with asymptotes, very little with the curve sketching, because actually your only application for that is your inventory problem, and they're real simple asymptotes. Okay, all right, so now we want to go to the first derivative, because we need to know about increase and decrease in possible extreme points. So we're just going to get increasing, decreasing, or where your derivative is 0. Okay? All right, so first derivative is, what is it? 2x minus 1. All right. So what we have to do to solve this is first set it equal to 0 so we know our boundaries for greater than 0 and less than 0. So the first thing we do is set equal to 0. So when x is equal to 1/2, we're going to have what? A possible extreme point. Possible extreme point, correct? 2x minus 1, x is 1/2. How do you find the y value when x is 1/2? Where do I put it? You have to plug it in the original, right? In this, the graph you're plotting, we're just using the derivative as a tool. This is a tool for increasing and decreasing, but this is the actual graph, x squared minus x minus 6, that I'm plotting. So we got to get the y value. So we have 1/2 squared minus 1/2 minus 6. I'm going to go ahead and get a common denominator. 1/4 minus 2/4, 24/4. So that looks like minus, what, 25/4? Yep. All right. So I'm going to plot the point 1/2 negative 25/4. That's about negative 6 1/4. Okay, so 1/2 negative 6 1/4 right here. All right. Now, I'm just going to draw, to help me out here, a little horizontal tangent line there, because I got a possible extreme point. Now, we already know the answer to this question, but we're pretending that we don't. Okay, little horizontal tangent line at 1/2 negative 6 1/4. Can you see that? Everybody good? All right. Now, this is where we're going to come over and use our little sign chart. Sign chart. All right, we've got to check all around x equal 1/2. I'm using my tool here, which is the derivative, to tell me, does the curve increase or decrease? Is it going to go up or is it going to go down? At 1/2, that's where the derivative equals 0. So I've got to check on both sides of that. I'm looking for where's the derivative positive, where's the derivative negative. All right, so we'll pick a number bigger than 1/2. Okay, 1. And where am I going to put that 1 for my tool? Into the derivative. So if I put a 1 into 2x minus 1, what kind of derivative do I have? Positive. I have a first derivative greater than 0. What does that mean? Increasing, which means it goes straight up. All right. I'm going to go to my graph here. When x is bigger than 1/2, I'm going to send my curve straight up. I have no idea, well, except we really do, but we don't at this point supposedly know anything that except that it goes straight up. We don't know the shape yet. All right, so we're just sending the curve straight up. All right, that's an increasing. Got it? Okay, let's get a little bit bigger than 1/2. An easy number is 0. Anytime we use 0, that's easy. And we're using our tool, the derivative. If we put a 0 in for x, we get 0 minus 1, we get negative. So we have, where do you want to put it, down here? A derivative less than 0, which means decreasing. So for all values of x less than a half, my curve comes down. Everybody good? All right, so when I'm less than a half, we have to have a curve that's coming down. So at this point, we pretend we don't know the shape. We just know it's going down. So I just kind of sketch lightly going down to going up. All right, now what can we say about our possible extreme point? If it went from decreasing to increasing, we have found a minimum. And basically, we think it's a relative minimum, but now that we know the curve never goes back down again, this will be our absolute minimum. What is the minimum value of my function here? Minimum value of the function, that's terminology. Okay, the minimum value is the negative 6 1/4. It occurs at the point 1/2 negative 6 1/4. So when we're doing optimization problems and we want the minimum surface area, well, that's going to be the minimum value of the function because it's going to be a surface area problem. Okay, it will occur for some particular dimensions. All right, value of the function is your quote y value. All right, everybody good with using that first derivative? Now, let's put some shape to the graph. I guess we'll go to the next page. First derivative was, what, 2x minus 1? I already forgot. Yeah. Okay. Now the third step is let's use our tool again and go to our second derivative. The second derivative is 2. Not much work for us. The second derivative tool is going to give us shape to the graph. All right, when you have a second derivative, which is a positive 2, 2 is greater than 0, what do we know? Concave up. Concave up. All right, sometimes you'll have a variable in it because that's the only way you're going to get changing concavity, right? And you have to solve for that x where the second derivative is 0. Here it's just a positive 2, so it's always concave up. All right, so now we're ready to put shape to our graph. We've got to hit these points. It's got to always be concave up. It happens to be decreasing concave up to increasing concave up. Do you see your nice little parabola here? Sketch over, hit all the points. And make sure they're not little straight lines. Okay, how's that? Pretty nifty, isn't it, that you can use the derivative for curve sketching? Answer that yes, yes, yes. Love it. All right, ready for another problem? All right, if you follow my little steps, it usually helps. Start out with your domain, y-intercept, and any x-intercepts if easy. Use your first derivative for going up or down, or possible extreme points. Did this one have an inflection point? No, because there was nowhere the second derivative equals 0. All right, and it was just concave up. All right, here's our next example. Let's see. Should we just jump right in and do a hard one? I think we can do a hard one, don't you? All right, so this one I'm going to go ahead and label hard. It's for all of you who are sleeping and think, whoa, this is hard. All right, but I think we can do it if we follow our steps. All right, we want to use derivatives to sketch. Whoops, the graph. Okay, sorry, I'm about to get sloppy there. All right, f of x equals. Really hard or kind of hard?
Very hard, go ahead.
All right. Okay, we'll try the hard, and if you start getting a little bit confused, we'll finish it, but then we'll go back to an easier one, okay? If you can do hard, then that makes the easier ones look really easy. Okay, so hard, here we go. 3x to the 4th minus 2x cubed minus 12x squared plus 18x plus 15. 3x to the 4th, and I sure hope I copied it down correctly. 3x to the 4th minus 2x cubed minus 12x squared plus 18x plus 15.
Is the domain always like all real?
The domain here is all reals because there's not a single value of x you can put in here that makes division by 0 or negative under the radical. So I'm taking her question, which was, is your domain always real? If you had a function f of x equals 1 over x minus 2 plus 7,
Then 2 would.
2 is not part of the domain. You have a vertical asymptote. Or if you have f of x equals the square root of x minus 3, your domain is x has to be bigger than 3 under the set of real numbers, because otherwise you get a negative under the radical. Okay. Everybody good? And then I need to add one more thing that you didn't want. In real problems, sometimes your domain has to be x greater than or equal to 0 because you could not produce negative 7 items. So in your application, or if you have a ship, a cruise ship, and it only holds 200 people, then you got to cut it off at 200 because you wouldn't want to crowd in 1,000 people on a 200 ship, or you get no business and it sink or whatever. Okay. All right. So let's draw our coordinate system here and see what we can sketch. This one's going to be fun. We may have to do some little breaks in the graph here because you already see a y-coordinate here is 15. Let's see. Let's just put on the x, and we may have to do some little breaks here. Okay. Alrighty, we're going to do the same way that we just did a second ago with our little 3-step process. All right, first thing we want to check out is any restrictions on the domain. Is there a y-intercept? Is there any vertical asymptotes, which there are none in here? Are the x-intercepts easy? And what would you say? No, definitely not. And we can also analyze one more thing in this. We can look at the end behavior, of our graph, because we know it's an x to the 4th. Okay. All right. What is my domain here? All real numbers. What is my y-intercept? 15. Okay, because I don't really know how all these points are going to come into play, but I do have just a little bit of an idea here because I jotted a few things. I'm just going to mark this as a 15. We're just putting all kinds of little breaks on the graph. And here's my 15. Okay? All right. There are no vertical asymptotes because there's no place in the denominator of a rational expression that makes it equal 0. And there's not, as x gets really big, so does the function. So it's just going to fly off to infinity. Okay, the limit as x approaches infinity, that would tell you if you had a horizontal asymptote. All right, the x-intercepts, not easy, so don't even spend your time. Not easy. Okay, but what do you know about the end behavior of this graph? As x gets really big or really small, this is the term that the graph starts to look like when you're way out there. So what does a x to the 4th look like way out there on the edges?
Always positively large.
They're always positive and going up, right? A x to the 4th kind of looks like a squished out parabola. They're always going to go up. So my end behavior here is that, I'm just going to do it like this so that we'll just have an idea. We know the ends of the graph. We don't know exactly what's happening in the middle yet, but we know on the ends they're headed off to positive infinity, both sides, okay, because it's like an x squared. All right, looking at the main term there. All righty, we're ready to start doing some graphing. What's the next thing we need to do, everybody? Find the derivative. Okay, so we're going to take the derivative and we get 12x cubed minus 6x squared minus 24x plus 18. All right, now I did this ahead and factored it for you, and if I gave you a problem like this on a test, I would give you the factored form for these things because you would be there way too long. Actually, this came off a test, and it's on your Vista site as an old test. So the factored form for this is 6 times x minus 1 squared times 2x plus 3. 6 times x minus 1 squared times 2x plus 3. Okay, I would give you the factored form of something that's this difficult. Okay? All right, I know. I don't want you here all day trying to factor this. All right, what am I going to do with this first derivative? I'm going to set it equal to 0 to look for some possible extreme points, and then I'm going to go to my sign chart to know if it goes up or down. All right, so possible extreme points will be where x is equal to 1. 6 can never be 0. X is 1, or x is minus 3/2. All right, I did this ahead of time. When x is 1, the y value, where am I finding this y value? It has to go back to the original because that's what I'm actually plotting. Don't forget the first derivative is only a tool. It's not giving you points on the graph. It's only telling you if it's going up or down. All right, when x is equal to 1, the y value turns out to be 22. When x is equal to negative 3/2, plugging that back into the original function, the y is going to be rounded to approximately a negative 17. Okay, it's not exactly negative 17, but so that we can get the graph going, that's what it is. All right, so let's get those points on our graph. 122 should be not too far from 15. So this is 122. Minus 3/2 would be right here, and negative 17 would be somewhere right here. So this is approximately, it is definitely negative 3/2, and negative 17 is approximately right here. Okay? Now, what kind of little line am I putting through 122 and negative 3/2, negative 17? In my graph, that's where the first derivative equals 0. So what am I going to put there? Little horizontal tangent lines. Okay, because we have some possible extreme points here. We don't know for sure they are extreme. They're only possible extreme. Okay? Wake him up. Go get some water. Want to jump, do exercises? Okay. All right. Now, what are we going to do with this tool? Tell me. What am I going to come over here on the side and do? Little sign chart. Okay, remember these are only possible extreme points. I need a sign chart to help me out. So we're going to plot where x is negative 3/2 and where x is 1. Okay, these are the only two places where the derivative is exactly equal to 0. Exactly equal to 0. Now we want to see where the derivative is positive or negative. All right. It's going to be easiest if you put it in the factored form. I think you can tell that. If you pick a number bigger than 1, such as 10, pick a number bigger than 1, like 10. What is this derivative? Positive. We have a first derivative positive, which means the curve goes up from there. All right. I don't know when you want to mark it, but you could just go like this. It's going up. Okay. When x is bigger than 1, it's going up. All right, let's pick a number between minus 3/2 and 1. What's the easy one? 0, yep. If you put a 0 in here, what happens? Put a 0 in for x, what happens?
It's positive.
Positive, because you're going to square that negative 1. That's positive. And then that's going to be a 3. So you still have a first derivative greater than 0. Increasing. Okay? So, from minus 3/2 to 1, I got to hit that 15 there somehow. Okay, this is going to be a bad graph. Woo. All right, but anyway, we know we're going up. Probably should have spread that further away, because if that's 15, Yeah, should have probably put it right here so it'd be more in line. All right, but anyway, you got this going up. Everybody see that? Okay, let's pick a number less than -3/2, such as, okay, -2. All right, you know when you square something, that's always positive, so I don't have to worry about that. If I put a -2 in here, you get negative, so we have a first derivative less than 0, so it's going to be decreasing. Okay, got it? All right, so when we're less than -2, it's decreasing, so my graph looks like this. All right, so the graph pretty much goes like this and like this. All right, now we need to put some shape to it. Oh, have we found an extreme point? Yeah, we only found one when it went from decreasing to increasing. This is going to be, actually, because the ends are now going to go up, we found an absolute minimum. What is the minimum value of this function, everybody? -17. Okay. It looked like 122 might be an extreme point, but when it goes from increasing to increasing, it just means I have a little horizontal tangent line there. Okay? All right, everybody good? Let's go now to the second derivative. You have horizontal tangent line still at 122. You still have a horizontal tangent line here because that's where the first derivative equals 0. So it's really going up, and then it has to have a little horizontal tangent line, and then it goes on.
So does it like level off or something?
Yeah, it does level off. And once we get our shape, we'll see how it levels off. Okay? All right, let's go to the next tool we have, which is the second derivative. Are y'all doing good on this? This is not bad, is it? All right. Now we want to do part 3. We want to use the tool of the second derivative. And now I've got to go back and see what it is. Second derivative is going to be, what, 36x squared minus 12x minus 24. Okay, and I know you could factor that one, but I'm going to factor it for you because I already have it. This factors to 12 times x minus 1 times 3x plus 2. Okay, 12 times x minus 1 times 3x plus 2. Okay, now what are we going to do with this second derivative? Set it equal to 0 to find possible inflection points. Okay, where it's set equal to 0 is at x equal to 1 and x equals -2/3. Setting each factor equal to 0. We're going to find the y value, the point on the function that goes with this. Remind me, where do I put the 1? Back into the original, because you're looking for the y with that. And we've already found that when x was 1, y is 22. And when x is -2/3, putting it back in the original, I'm just going to round that to a -1. I'm only doing this so that we can get on with the problem. Okay. All right, so these are possible inflection points. Again, it's possible. We don't know until we check it out. Okay? All right, so now we're going to check all around. -2/3 and 1. 2/3 and 1. Okay? All right. I'm looking for now concavity. Concavity. All right, if I pick a number bigger than 1, where am I going to put a number bigger than 1, such as 10, to check concavity? Into the tool, right. So if I pick a number bigger than 10, I'm going to put up here in the second derivative. Is that going to be positive or negative? Positive. So we have a second derivative greater than 0, which means concave up. Okay? All right, so let's go. Oh, I forgot to plot the point -2/3, -1. Negative 2/3, negative 1 is going to be exactly right here. Okay, that's negative 2/3, negative 1, right there. Okay, sorry. All right, so when x is bigger than 1, it's going to be a concave up. So here is 1, here is bigger than 1, it's concave up. How am I going to draw this graph? Like a little parabola up there going up, but just from right here. So we'll just do like this. Okay, there's a little concave up increasing. Okay. All right, let's go to the next part of our graph. From negative 2/3 to 1, in this interval, what's an easy point to use?
0.
Good, 0. We're going to put in our second derivative. So when I put in my second derivative, what do I have here? Negative second derivative. Negative 1 times 2 times 12 is negative. So I have a second derivative, which is negative. And that's going to be a concave down. Everybody got it? All right, so from negative 2/3, which is right here, to positive 1, we got to draw a concave down. It's going to be increasing concave down. So my bad units here really did work out good for me. That's a real obvious concave down. Okay, see how I traced right over it? Concave down. Okay. Have I found an inflection point, by the way? Yeah, for sure. This is an inflection point, yes, because it goes from concave down to concave up. All right. Now let's look less than negative 2/3, such as something like negative 10. If I put a negative 10 in here, what's it going to be? Negative times a negative, which is a positive. So it's going to be a second derivative greater than 0. It's going to be a concave up. So for all values less than 2/3, negative 2/3, we're going to come back and sketch a concave up. So here is negative 2/3 and all values less. This is a decreasing concave up, increasing concave up. So I'm just going to kind of sketch around the graph here and make it like this. I found another inflection point, yes, because it went from concave up to concave down to concave up. Okay? So this is also an inflection point. We have 2 of those. All right. Now, aren't you proud of yourself? You did it. But you've got to be careful to do one step at a time, and I think my steps are good. Check out your domain, get your y-intercept. Look at the end behavior of the graph. If the x-intercepts are easy, do it. Then use that tool of the first derivative, just tell you if it goes up or down. You don't know a thing about the shape until you get into your second derivative. All right, what questions can I answer about this particular problem? Anybody? Everybody?
Why is the first one an inflection point? I get why the bottom one would be, but...
This one's an inflection point?
Hey, you said there was 2 inflection points.
Yes,
there.
this one right here, because it went from concave up to concave down. That's an inflection point. And this one, because it's concave down to concave up. This is a absolute minimum point down here. Is that the answer to your question?
Well, why wouldn't... Oh, okay.
This one wouldn't be an inflection point because it's concave up all around it. That made it a minimum. It went from decreasing to increasing. That's what made it a minimum. Everybody good? Okay, I think what I'd like for you to do is to start working in your homework problems on 2.3 and 2.4. And a lot of times they're going to take some little bits and pieces and ask you information. Let me flip through these. I'll come back. Don't let me forget. Tomorrow we'll take another problem from the top. And I'm going to go ahead and get you started in the optimization problems. Okay, I'm just going to flip through the pages in the book, 2.3, to make sure I've covered it all. Okay, on page 163, we're looking for possible extreme points by setting that first derivative equal to 0. That's what we did. And then at the bottom, the first derivative test. You're setting your first derivative equal to 0, and it's telling you if it changes, the derivative changes from positive to negative, you got a maximum. That's increasing to decreasing. Flipping the page, I'm sure they wanted to tell you the vice versa, but they apparently didn't. Oh, the rest of it, page 164 in the middle. If it goes from negative to positive, first derivative, you're going to have they're calling it local. Another word for that's relative. Relative extreme, local extreme. Remember, it's got to be in a little interval there. If your sign does not change at A, we just saw one where the sign didn't change at where the derivative, that went from increasing to decreasing. If the sign doesn't change, then it's not an extreme point. Here's a good example. One, I would invite you to cover up the work, use your derivative, and locate your max and min points. This kind of does one little step for you at a time here. Here's their sign chart, much more elaborate than me. I take the places where the derivative is equal to 0, and we mentally looked at each factor and multiplied like a negative times a negative, and we got our positive. So I didn't write out every little detail on the sign chart. Obviously, my little sign chart looked a lot simpler than this. But this is theirs, where they put in every little detail for you, which I think is a good thing. Okay? Although I don't do it that way. All right. Second derivative test on page 167. Second derivative test. Let's see what it says. If your first derivative is 0, that's that horizontal tangent line. And your second derivative is negative, which means concave down. All right, so I didn't mention the second derivative test for extreme points. If you had a horizontal tangent line at a point and it was concave down around that point, that would have to be a max. If you have a horizontal tangent line, first derivative equals 0 to point, and then your second derivative at that point is positive, that would have to be concave up there, so you would have a minimum value. So horizontal tangent line at a point, and it's concave down there, max. First derivative horizontal tangent line, but second positive, concave up, you'd have a minimum. That's called the second derivative test for extreme points. So if you didn't want to go through the first, which is increasing to decreasing or decreasing to increasing, you could use your second derivative test. I usually just use the first derivative test because I got to sketch the graph anyway and get there. Okay, page 169 at the top is talking about looking for, what's that word right there? Possible inflection points, and you do that by setting your second derivative equal to 0. Again, you got a lot of great examples in here for you. Okay, and then it just gives you tons of problems in the exercises, but what they do in the exercises is just give you one little piece at a time, like find your relative max and mins. It tells you it has one relative max and min, find them. Then down at the bottom in problems 25, I think this is where you really should be concentrating. Sketch the curves locating your relative extreme points and inflection points. I would say jump on these kind of problems so that you're going through your process for your curve sketching. Okay, and then let's see what's in 2.4. 2.4 is just more curve sketching. Oh, in section 2.4, they remind you of the quadratic formula. If you had a quadratic function, and it didn't factor, and you were looking for the x-intercepts, you could use your quadratic formula to find those x-intercepts. And their first example here is a quadratic function. And when you start looking for the x-intercepts, that one does not factor. So if you used your quadratic formula, you could find out where it crossed the x-axis. And they tell you right here, it's not easily factored. So we use the quadratic formula. Okay? No, I usually, when we're curve sketching, I don't ask you to find the x-intercepts if it's requiring a quadratic equation, because then you got to go, okay, square root of 2 is about 1.4. I got to approximate what it is anyway. I just say find the x-intercepts if they're easy. Okay. I don't call that one easy. If it factors, just do it. Makes you a little easier sketching your graph. Okay, here's an example of one similar to what we just did, where it had looks like your tangent line crossed through the point 3,7, so you know that's an inflection point, but I believe the way the curve goes, you've got a horizontal tangent line there too. Okay. All right. A little bit with asymptotes. I'll just tell you about this to look at it. We don't do a lot with asymptotes in Math 131. This is just a simple function x over 1 plus x. Where are you going to have a vertical asymptote right away? Where's this function undefined looking at your domain? Right, x equal to 0. All right, so you have a vertical asymptote at x equal to 0, but they're going to restrict it to x being bigger than 0 anyway. So it's really defined for all values of x greater than 0. You have vertical asymptote. They took their first derivative. They take their second derivative. First derivative set equal to 0. You really, x squared equal to 1, you know that's x equals 1 or negative 1. I like to put it like this. When you have a quadratic, if you write it all on the same side, you don't ever lose any factors. So that's x plus 1, x minus 1 equals 0. But the reason you're not going to use x equal negative 1 is because of your restricted domain. Okay, so to me that looks a little bit not so good, because if you were solving x squared equals 1, it really is x equals plus or minus 1, but you're going to leave out x equal negative 1. Okay, square root principle there. All right, and when you come to the top of the page here, they just used the first derivative to find that it was decreasing to increasing around that 1. And then they did a second derivative and found out, you can look at the second derivative and tell that's always positive when x is positive. So it's a concave up. So it went from decreasing to increasing, concave up, and there's your graph. Okay? And that's about really as hard in curve sketching as it gets in Math 131, because that kind of relates to inventory problems. All right, are we good, good, good? Okay, so play, and enjoy. You got lots of exercises in 2-4. Sketching graphs. You can do tons of those. Be sure you look at the homework set, though, because I've probably carefully picked out some problems for you to do here, the homework set that I gave you. All right, we are ready to go to some optimization problems. So we're in sections 2.5 today, 2.6. Okay, oops, running out of paper. I think I'll start a new one. All right. You need to work, work, work. All right. You will probably have about half of your next test, 40 to 50% of your next test will be optimization problems. This is like the grand finale. Why have we done all this work? Well, we've done it so that we can learn to apply it. So you want to work, work, work in these. All right. As I mentioned at the beginning, I have it separated into 4 types of problems you're going to be responsible for. One is geometric. And geometric means that we have rectangles, we have little rectangular boxes, we have little right circular cylinders, okay? And we also have cones, but I don't believe you have any problems with cones in it. So little geometric figures here. You want to be sure that you know, if you're talking about a rectangle, you want to be able to talk about the perimeter. What do you think about when you do perimeter of a rectangle? Just add up the sides, right? Add up around the outside. Area, what do you think about when area? Length times your width. All right, when you get to a 3-dimension, though, we talk about surface area, and we talk about volume. I'll just call this an X, Y, and an H. Okay, can you see my box? Here's the bottom of it. Here's the height. Okay, when you're talking about the volume in words, that just means how much does your box hold? How much does it hold? What's the formula for the volume here? Yes, length times width times height. The volume of anything that goes straight up, by the way, anything that goes straight up is easy to remember. You just get the area of the bottom and multiply times the height. So the area of the bottom in your box, you just got a rectangle. If you think of this room as a big rectangle, if you get the area of the bottom and multiply times the height, you've covered how much space in here is covered. So that's volume. All right, let's do surface area. I better do that in big part here. Surface area. All right, so let's pretend that this room is our box. And what is this box? Surface area means the walls and the floor. So we have a floor, which is the bottom of our box. So we'll look at the area of the bottom. You can put it in words. A lot of times it's easy to come up with a formula. You got the area of the top, but if this is a box that goes straight up, your box is going to be the same. So we got the area of the bottom and the top. Okay, and then we have the two sides over here. If this box is a rectangular box, they're going to be the same sides. Two sides. And then I'll just call this front face and back face. Front face and back face, they'll be the same. Front and back face. Does that make sense? We're going to look at the areas of each of these parts. All right, so go to my little box here. What's the area of the bottom of this box? X times Y. So we have a bottom and a top. So this will be 2 times XY. Okay, now let's go to the sides of our box. I'll try to do that in yellow. Here's a side, and here's a side. What's it? YH. Does everybody see that's a YH? And we have 2 of those. Is that going to show up in yellow? Yes. Okay, and now let's go to the front face and the back face of our box, which is this little part right here in the back. And this little part up here at the front, which is the same, which is X times H. Do you see it? So I have plus 2XH. Okay? So that would be surface area. And I think maybe a couple problems will say a box with no top. So if it's no top, then you just have a XY here. Okay, so you have to look and see if it has a top. Everybody good? Okay, now let's go to our little right circular cylinder. Same deal, we want to talk about a surface area, and we want to talk about a volume. Okay, the volume is always easy because you look at the bottom of your thing, whatever it happens to be, get the area, and multiply times the height. So when you look at this can, what is that bottom? What kind of figure? It's a circle. So the area of a circle is pi r squared. And then to get the volume, you're going to multiply that times the height, h. Okay, pi r squared h. And your volume will come out in cubic units because you got your radius square. So that's square units. Height is units. Unit squared times units. It gives you your cubic units for volume. Okay, let's get our surface area for our... Okay, that's that little part. Let's go to the next page for surface area. Okay, we got our little right circular cylinder. And let's get the surface area. This means how much materials it's made out of. Here's the radius and here's the height. All right, when you think of our can, it has a top and a bottom, correct? So we have the area of the top and bottom plus the area of that round part. Is that correct? Okay, what do you want me to call that? Area of round part? Outside of can?
Yeah.
Outside of can, or whatever it is. All right, So let's get the area of the bottom. When you look at that bottom, that's a circle. The area is pi r square. You got a bottom, you got a top. So the area of the top and bottom is 2 pi r square, right? Okay. Now, this is the easiest way for me to see around the outside of the can. So here is my can without a top and a bottom. Okay, can without a top and a bottom. What happens when I slice this can? It becomes a little rectangle. So if I get this and multiply it times this, I got it made, right? Well, that's the height, so that's easy. All right, but if I have it together, what's this little thing right here called? Circumference of a circle. What's the formula for the circumference of a circle? 2 pi r. Okay, so when I cut it, that's still 2 pi r, right? So this area of this part is going to be times h. So 2 pi r, that's the top part of this can that was the circle, for the height of h. So surface area begins to be a formula that's not too hard to deal with. Okay, everybody good? Alrighty, so the first type of problems we're going to look at are geometric. And let's see if we can start with one today. We'll pull an easy one, and then we'll pick up here tomorrow. All right, I'm on page 187 in the book. Page 187, and we're going to start with number 20 because that looked the easiest to me. All right, so when we're going to do optimization problems, we've got to come up with the function that describes the situation, and we're looking for the function that says we need to maximize it or minimize it. That's what we're going to be taking a derivative of, right? So let's go to problem number 20. I'm on page 187. Area. Find the dimensions of the rectangular garden of greatest area. The reason I picked this is because it looks like a pre-calculus question. You could do it with pre-calculus, but this will get us started. We're going to use derivatives. Your test says use derivatives. If you don't use derivatives, you don't get credit. We're using the tools that we're learning in calculus. Find the dimensions of the rectangular garden of greatest area that can be fenced on all 4 sides with 300 meters of fencing. All right. When you read a problem like this, I highly, highly recommend that you first focus in on what it is you need to maximize or minimize. What do I need to maximize here? Area. So I've got to come up with a formula for area. I'm going to maximize area means I'm going to be taking a derivative of an area function. Now, the area of what kind of figure? A rectangle. Okay. So our focus is first on getting that function we've got to take a derivative of. So the big deal here is that I'm going to have to do the area of a rectangle, and this is what I need to maximize. I keep writing myself that says max, M-A-X, area of a rectangle. I keep focused on what the function I need is that I'm going to take the derivative of. All right, then the rest of it is called a constraint equation, because every rectangle in the world, the formula is length times width, right? We're not trying to maximize the area of every rectangle in the world. We want a rectangle that we can only use 300 feet of fencing on. So we have a length and a width, and you have to read the problem carefully. This fencing is going to go on all 4 sides. Sometimes you have it only on 3 sides because you're next to a river or a barn. I'm sure you've seen all those problems. So I have a restriction or a constraint that I'm going to use exactly 300 feet of fencing around here. Give me the formula going around the outside of this rectangle. What is it going to be?
Add up on the side.
Okay, so when you add up all the sides, you're going to get what? 2L plus 2W equals 300. If I can get this a constraint equation into what I need to take the derivative of, then I have restricted my rectangle to one that has 300 feet of fencing. Right now you're on every fence in the world. I mean every rectangle in the world. So it really doesn't matter which I substitute. Let's make life easy and divide through by 2, so we get L plus W equals 150. I'm just going to pick W to be 150 minus L, 150 minus L, and I'm going to now send it to my equation over here. The area that I'm going to need to maximize, L, and in the place of W, I put 150 minus L. Area is 150L minus L squared. All right, so this is my formula for area in terms of length of my rectangle. If you were graphing this, along this axis you'd have L, along this axis you'd have area. You can already see that this is a parabola that's going to open down, So wherever your vertex is, that's where you're going to find your maximum area, correct? You already know how to do this problem, but we're going to use derivatives. All right, so in order to maximize something, I'm going to take the first derivative, set it equal to 0, because that's my possible extreme points. So I'm taking the derivative of A with respect to L, and I get 150 minus 2L. How do I find possible extreme points? Set the first derivative equal to 0 for possible extreme points. All right, so when I set this equal to 0, L is equal to 75. Just because the first derivative equal to 0, is that going to guarantee me when the length is 75 that gives me a maximum area? No, I need to do my little first derivative test. Okay, if I pick a number bigger than 70, I'm using my tool, the derivative, to go for increasing, decreasing. All right, a number bigger than 75 into 150 minus 2L, that tells me negative, decreasing. Pick a number less than 75. Of course, we got to be bigger than 0, right? Because we're really actually talking about a physical thing here. We got to have a length on our fence. So pick a number like 1. Positive. So it goes from increasing to decreasing. So have I located an extreme point? A max. And what am I looking for? Dimensions that maximize the area. Okay, so hey, we got it made. Length is 75. And this turns out to be a square because the width is also going to be 75. Anytime you got a rectangle, if you want to maximize your area, you're going to have a square anyway. That's the way you're going to come up with the biggest area there. All right, so my dimensions are 75 meters by 75 meters, and that will max out my area. Everybody good? We're going to have to stop here. We're going to pick up with these tomorrow. Very important you get a good night's sleep because optimizations you have to be alert on. Make it a great day, everybody.